Tonight, look up at the moon. It seems fixed in the sky. It has followed Earth for billions of years, controlling tides, lighting the night, and appearing so perfectly sized that it can completely cover the sun during an eclipse. But the moon is not staying where it is. Every year, it moves a little further away from the Earth. Not enough for you to notice, not enough for any human lifetime to notice, but enough that scientists can measure it. The moon is currently retreating from Earth by about 3.8 centimeters every year. That is roughly a speed at which your fingernails grow. It does not sound like much, but the movement has continued for extremely long time. And as the moon moves away, it is quietly changing Earth. Our days are getting longer, our tides are changing, and one of the most spectacular sights in the sky will eventually disappear forever. So why is moon leaving? And could Earth ever lose it completely? To understand that, we need to look at something that happens every day: the tides. The moon's gravity pulls on Earth. It pulls on the solid planet slightly, but its most visible effect is on the oceans. Water on the side of Earth facing the moon is pulled toward it, producing a tidal bulge. Another bulge forms on the opposite side. As Earth rotates through these bulges, coastlines experience rising and falling tides, but the bulge do not point directly towards the moon. Earth rotates once every 24 hours. The moon takes about a month to complete the orbit. Because Earth spins much faster than the moon moves around it, Earth's rotation carries the tidal bulge slightly ahead of the moon. That small misalignment changes everything. The moon pulls backward on the bulge. This creates friction that slows Earth's rotation. But gravity works both ways. The bulge also pulls forward on the moon. It gives the moon a tiny gravitational push along its orbit. The moon gains orbital energy. And when an orbiting object gains energy, it can move into a higher orbit. So the moon moves further away. This can sound backwards. You might expect that giving the moon more speed would make it escape immediately. Instead, the moon rises into a larger orbit when it moves more slowly around Earth. The same basic principle is used with spacecraft. A carefully timed push can raise a satellite into more distant orbit. Earth is effectively doing this to moon continuously. The energy is not appearing from nowhere. It comes from Earth's rotation. Earth loses rotational energy. The moon gains orbital energy. The result is that Earth spins slightly more slowly while the moon drifts slightly further away. This means that the length of the day is not permanent. Hundreds of millions of years ago, Earth completed a rotation faster than it does today. The day was shorter. Over immense periods, the moon's tidal influence slowed the planet until our day reached its current length. The slowing continues today. Although many other effects also cause small changes in Earth's rotation, the moon's retreat is tiny. So, how can we possibly measure the change of only a few centimeters across a distance of roughly 385,000 kilometers? The answer is sitting on the moon. During Apollo missions, astronauts placed special reflectors on the lunar surface. Other reflector arrays were later carried there by Soviet robotic missions. Scientists on Earth fire powerful laser pulses toward these reflectors. Most of the light misses, but a tiny fraction hits the reflector and returns to Earth. By measuring how long that round trip takes, scientists can calculate the moon's distance with extraordinary precision. Light takes a little more than 2.5 seconds to travel from Earth to the moon and back. Repeated measurements over decades reveal that the average distance is increasing by about 3.8 centimeters each year. The moon is leaving, but there is no reason to panic. It will not suddenly break free next year or in a million years. The current retreat rate is not necessarily a fixed speed that can simply be multiplied forever. Earth's continents move, the oceans change shape, water depth changes. All of this affect how efficiently tidal energy is transferred. As the moon moves further away, its tidal influence also becomes weaker. Its retreat gradually slows. The long-term future is therefore more complicated than drawing a straight line from today into eternity. But the consequences are still real. As the moon gets further away, it appears slightly smaller in our sky. Right now, the sun is about 400 times wider than the moon. But the sun is also about 400 times further away. That coincidence makes the two appear almost exactly the same size. When their alignment is perfect, moon can cover the bright surface of the sun and reveal its faint outer atmosphere, a total solar eclipse. But the moon's orbit is not perfectly circular. Sometimes it's closer to the earth and appears larger, sometimes it further away appears smaller. When the moon is too far away to cover the entire sun, it leaves a bright ring around its edge. This is an annular eclipse. As the moon continues retreating, it will appear smaller more often. In the distant future, it will no longer appear large enough to completely block the sun. Total solar eclipse will end. Future observers may still see the moon pass in front of the sun, but they will only see the dark circle surrounded by a ring of light. They will know that total eclipses once existed, but none of them will ever experience one. The tides will also weaken as distance grows. The moon will still influence Earth, but less strongly than it does now. Earth's rotation will continue slowing, and the length of the day will continue growing. In simplified far future version of the Earth-Moon system, Earth could eventually rotate once during the same time the Moon takes to orbit. Earth would then always show the same side to the Moon, just as the Moon already shows nearly the same side to the Earth. From one half of the planet, the Moon would hang up in almost the same region of the sky. From the other half, it would never be visible. But the real solar system may not survive in its present form long enough for that final state. The sun will change dramatically over the next several billion years. Its increasing brightness and eventual expansion will reshape the Earth and the Moon long before a perfectly stable tidal ending can be guaranteed. So, will the Moon ever completely leave the Earth? Probably not through the slow tidal process alone. Its retreat weakens as it moves outward, and before it could simply wander away into the deep space, the entire Earth Moon system would face much larger changes caused by the aging sun. The moon is leaving, but not like someone walking out through the door. It is more like two dancers slowly extending their arms. They remain connected, they simply move further apart as one of them gradually slows down. And this has been happening above us for billions of years. Every tide moving across an ocean transfers a tiny amount of Earth's rotation to the moon. Every day is slightly longer because of that exchange. Every year, the moon is slightly further away. The change is almost impossibly small, but given enough time, tiny changes can reshape worlds. The moon you see tonight is not exactly where it was when the first humans looked up. It was closer then. It appeared slightly larger, and far in the future, it will be smaller than it is now. The moon has been beside Earth for almost our planet's entire history. It may feel permanent, but nothing in space is completely still. No planets, no stars, not the galaxies, and not even the moon that seems to follow us every night. It is already moving away at roughly the speed your fingernails grow.